So we've done a lot of integrations, some of which we've had definite integrals and some of which we've had indefinite integrals. And indefinite integrals are those where we do not have limits of integration and we get answers like sine of x or natural log of x or e to the 2x plus 3 or whatever it may be. But in the definite integral cases, we have limits on our integrations. And that's fine, and we plug those numbers in and see what happens. But we can also have what are called improper integrals, where our limits of integration could be something that creates a problem. For instance, one of the limits of integration could be infinite. So if we had this integral, we would say, well, that's an easy integral to solve. We raise the power by 1 and divide by it. And of course, for completeness sake, since it's an indefinite integral, we put this plus c. But if I take that same integral, and if instead of saying it's indefinite, I put limits like this, and say that's the integral from 1 to infinity. Well, I look at that and I say, well, I remember something about integrals having to do with area under the curve. And if I go infinitely far, isn't there going to be infinite area under the curve? So this is going to get me in trouble. In fact, if I raise this to the power and divide by it, and then say I need to evaluate this at infinity and 1, then I would have infinity to the 4th power over 4, which of course is an infinite. So that's what we would call a divergent integral. Now, that's not actually the way that we look at this. We are careful and we say this is an improper integral, so we don't want to write it that way. Instead, we want to say, okay, we want an integral that goes from a number to another number, and we're going to say that number is a. And we're going to say we're going to take the limit. After we do the integration, take the limit as a approaches infinity. Okay. And we do this, and we say, okay, the limit as a approaches infinity of x to the 4th over 4, evaluated at a and 1, looks like 9. Limit as a approaches infinity of a to the 4th over 4 minus 1 to the 4th, which is 1 over 4. And everything's okay up to that point, and a could be something else. If a was 12, this would be fine, right? The fact that it's infinity, when I plug it in there, then I have a problem. And then I say, okay, since that becomes infinite, then we would say that that integral diverges. Now, at first thought, you think, well, obviously anything that goes to infinity is going to be of this type and diverge. Why do we even bother to talk about it? Well, there are integrals that, even though the limits are infinite, we are able to do. So let me do one of those. Let's make a very slight change here. And let's instead say, okay, instead of this, 1 over x to the 3rd. Now, things we need to look at, in addition to just the limits, we could also have an improper integral where, for instance, if this went from minus 1 to infinity, there's a problem here at 0. We would have to be careful at that point, okay? But for this one, we would say, well, first thing I'm going to do, I'm going to rewrite this a couple of ways. I'm going to say limit as a approaches infinity of the integral from 1 to a of x to the minus 3 dx, because now that's in a form that I know just what to do with. I raise the power by 1 and divide by it. So again, the limit as a approaches infinity. Up to the power by 1 and divide by it, I get x to the minus 2 over minus 2, which needs evaluated at a and at 1. And that is the limit as a approaches infinity. Whereas x to the minus 2 means that there's a minus 2 on the bottom. So I'm going step by step here. I would have a negative 1 over 2x squared is really what this is, just another way of writing it, which I want to evaluate at a and at 1. Limit as a approaches infinity. It's a negative, not an equals. I have negative 1 over 2a squared minus a negative 1 over 2 times 1 squared. And I would then rewrite this and say minus and minus makes a plus, so that makes 1/2 minus 1 over 2a squared. And finally, once I get to that point, I would say, now I'm going to let a go to infinity. Well, what happens when a goes to infinity here? Well, I still got 1/2. The a has no impact here. A going to infinity here makes this 1/2 minus 0. So the result is just 1/2. So even though it's an improper integral, this is a case where that improper integral is convergent. We would say it's convergent because it comes to some particular value. And really what that is, you know, if you think about what 1 over x cubed looked like, well, 1 over x cubed, the bigger x gets, the smaller this value is going to be, right? When x is 1, of course, this is just at 1, right? 1, 1. But when x is 5, for instance, 1 over 125, this is rapidly going down like this. And so even as you go to infinity, so much less, you know, smaller and smaller and smaller amount of area that's getting under that curve, it's asymptotically approaching the axis, and therefore it does converge.